All right, here we go. We're going to start with scientific measurements. Measurements are very important in chemistry, and numbers are very important in chemistry, and how to use them properly is very, very important in chemistry. So we're going to start with using and expressing measurements, and then the units of measurement that we use in science. In chemistry, you're going to encounter very large numbers or very small numbers, and you can work with them more easily if you use scientific notation. That number there, 602, followed by 21 zeros, atoms, can be written in scientific notation as 6.02 times 10 to the 23rd atoms. The coefficient is the number 6.02, and the power of 10, or exponent, is the 23. That means there are 23 spaces between the beginning of the number and that 6. 1.661 times 10 to the negative 24th grams is very small. That's the size of a proton. The coefficient in this number is the 1.661. The power of 10, or exponent, is negative 24. So when an exponent's very large, like 10 to the 23rd, that means a very large number. But when it's a negative exponent, that means it's a very small number. So if you were going to write 1.661 times 10 to the negative 24th as a regular number, that thing, that monstrosity you see at the bottom with all those zeros, 1661, would be the way to write it. In scientific notation, the coefficient is a number that has to be greater than or equal to 1 and less than 10. And the exponent is always going to be an integer. So the coefficient, the number in front, is going to be between 1 and 10, and the exponent always has to be a positive or negative integer. When you write numbers that are greater than 10, the exponent is going to be positive, and that equals the number of places the decimal point is moved to the left. So if I take 6,300,000 and I move that decimal from the right side between the 6 and the 3 to make it a 6.3, I will have moved it 6 spaces to the left. That's why the exponent is 6. 94,700, that decimal, when it goes between the 9 and 4, I'm moving 4 spaces to the left, so my exponent is 10 to the 4th, which means 10,000. 10 to the 6th means a million. Numbers less than 1 will have a negative exponent in scientific notation. The negative exponent equals the number of places to the right that the decimal would be moved. So a number like 0.000008 becomes 8 times 10 to the negative 6 because I'm going to move the decimal 6 spaces to the right. A number 0.00736 becomes 7.36 times 10 to the negative 3rd because I'm moving the decimal 3 places to the right. So if you move the decimal to the left, you're getting larger, meaning your exponent's going to increase. If you move it to the right, that means you're going smaller and the exponent is going to become a negative. Now, very important numbers in chemistry are called significant figures. And they're the numbers that you get in a measurement that include all of the known digits and one estimated digit. Measurements must always be reported to the correct number of significant figures because calculated answers depend on the number of significant figures in the values used in the calculation. So before we start doing any calculations, we're going to talk about how you figure out how many significant figures there are. So we have here, if we want to know how many significant figures are in a measurement, there's a few ways that you do this. And the first one is there's 2 situations in which numbers will have an unlimited number of significant figures. The first one involves counting. A number that is counted is exact. This measurement is a counted value, so it has unlimited number of significant figures. For example, if there are 28 students in a classroom, that's an exact number. You can't have a half a student. The second one is involving measures that are values that are found in conversion factors, like 60 minutes per hour, 100 centimeters per meter. Those have unlimited significant figures because you have 1 hour, exactly 1 hour, exactly 1 meter. So since they are exact, those are unlimited. Now we're going to talk about when they're not unlimited. So the first thing you have to do is, if you look at every one of the numbers on this page, you see that there's a decimal in the number. If there's a decimal in the number, you start on the left side of the number and begin counting the first number that is not a zero and then count to the end. So 717.03, 17.03 is going to have four significant figures because I start at the 1, I go to the 7, to the 0, and the 3. Now the second one's a little different. There's zeros on the left side. It says above that you start at the first number that's not a zero. So I start at the 1. So I go 1, 3, 4. That's three significant digits. The zeros on the left never count. But the next one, they do count because I start with my first non-zero, which is 1, and I keep going till I finish. 1, 2, 0, 0, 0. That is 5 digits because there's a decimal. I start on the left, and when I'm finished, I get 5. So right there, that 120.00 is 5. Then this next one, all those zeros in front of that 5 don't matter because you start on the first non-zero. So there's a 5 and a 2. So that digit is going to be a 2-digit or a 2 significant figure calculation. Now, when you are using exponents, it's very easy. The number that you see, because exponents have to start between 1 and 10, the number of digits you see is the number of significant digits. 135, that's 3. So 1.35 times 10 to the negative fifth has three significant figures. 6.02 times 10 to the 18th, the 6, the 0, the 2, that would be the same as 135. That is three significant figures. So if you have a decimal, you find the first number that's not a 0, and you count from there to the end. That's how many significant digits. Now, what if there are no decimals in the number? So if there's no decimals in the number, like 13,250,000, 1,000, 130, 300, 130 milliliters, sorry. If there's no decimal in the number, you don't start on the left, you start on the right, and when you hit your first non-zero, you continue counting to the left. So all those zeros in 13,250,000 don't matter. I start at the 5, and from the 5 to the 2 to the 3 to the 1, that's four significant figures. The zeros don't count because the decimal's not there. 1,000 grams, the first number, if I start on the right, the first number I hit that is not a 0 is the 1. So that's only going to be one significant figure. 130,300. I start at the 3 that's on the right. And then there's the 3, the 0, the 3, the 1. That makes four significant figures. Same thing with the 130. I start at the 3 and I go to the left. So the 3 and the 1 makes two significant figures. So, all right. We've got 123 meters. Since there's no decimal, I start on the right. 321, that's three significant figures. 40,506 millimeters. Since there's no decimal, I start on the right. 60504, that's five significant figures. 9.800. Since there is a decimal, I start on the left at the 9, the 8, and the 3 zeros. That's a total of 5 significant figures. 22 meter sticks, that's a tricky one because you're counting them. It's not two significant figures, it's an infinite amount because remember, counted values are exact. You can't have 22.3 meter sticks unless you break one. Okay. Letter E, I have a decimal, so I'm going to start at the 7. I'm going to skip the zeros. I'm going to start at the 7, go to the right. That's four digits. 7080, that's four significant figures. 98,000 kilometers, there's no decimal in that number. Since there's no decimal, it's the 9 and the 8. So that's only two significant figures. Now, if we are trying to do significant figures for long term, you're going to have to practice. So I want you to look at these and take a little time and tell me which rule am I going to use for A. So this is how you go about doing these. If I'm looking at A, I see a decimal, so I'm going to start on the left. I don't start until I hit a non-zero. That's a 5. 5730, that's 4. 8765, start on the right, 4. So that's all four numbers. All those zeros on the left don't matter. So I start at the 7. The 7 and the 3 makes for two significant figures. Now, there's a decimal in this one, so I start at the 4 and I go all the way to the right. The 4, the 3 zeros, and 7 makes a total of 5 significant figures. Now, a lot of times you'll be given digits, and a lot of times you have to estimate. You have to round numbers. So this is just like math class. We're going to round the exact same way. When doing calculations, we may have to round an answer. If the digit to the right of the last significant digit where you're going to round is less than 5, you just drop the rest of the numbers and leave it alone. For example, 314.721 is what my calculator gave me an answer. But when I look at my calculator and I see my numbers I started with, I can only have 4 significant figures because of the numbers. Because of that, I start at the 3 and I go to the right. When I hit the 4th one, it's a 7. The next digit is what I'm looking to see. Is it less than 5 or greater than 5? So since 2 is less than 5, I just chop off that 2 and the 1, and it goes 314.7 is my rounded to 4 digits. Now, if you wanted to do that in scientific notation, remember the number has to be between 1 and less than 10. So I move the decimal 2 to the left, so my exponent becomes a positive 2, 3.147 times 10 to the second meters. The second one's a little bit different. I want to round it to 2 significant figures, but the decimal's in there. So I start at the 1. I go to the 7. The next digit's a 7. Because it's a 7, it says up above, if the digit is greater than or equal to 5, we're going to increase the last digit by 1. So 0.001775 becomes 0.0018 or 1.8 times 10 to the negative third meters, because I would be moving the decimal 3 to the right to get between the 1 and the 8. Okay. All right, now I've got these numbers. They're in normal notation. I want them in scientific notation. So I'm going to have to move my decimal left or right to make it scientific, and I'm going to have to round it to the number in parentheses. So the first one is I want to make 0.00002235 liters scientific with 2 significant figures. So I start on my left. I find the first digit's a 2, the second one's a 2. There's my 2 significant figures. The number to the right of that 2 is a 3. So I'm just going to get rid of the 3 and the 5 and make it 0.000022. But how do I make that scientific notation? I move that decimal from the left to go between the 2 2's. So I go 1, 2, 3, 4, 5. So that puts the decimal between the 2 2's, starting at the left and moving. So that one becomes 2.2 times 10 to the negative 5th liters. That 9838940 seconds. I went 3 significant digits. So I start on the left. I see my 9, I see my 8, I see my 3, and I see an 8. So guess what? I'm going to make that 984, but I have to move the decimal. Now there's none given, so it's going to be assumed to be to the right of the last 0. So I start there. I go 1, 2, 3, 4, 5, 6, 7 to the left. So my number is going to be 9.84 times 10 to the negative 7, because the number after the 3. Now the next one, it's a small number, so I know my exponent's going to be negative, but I have to get the 0 between the 6 and the 5. Okay, I got that. So I go 3 to the right, it's 10 to the negative third. But I want 4 digits. So I have the 6, the 5, the 4, and the 3. That's 4, but after the 3 is a 7. So because it's 37, that's going to turn into basically 40. So my number is going to be 6.544, because that 7 behind the 3 makes the 3 become a 4. It jumps up. But it's still 10 to the negative third because I move my decimal 3 to the right. Now the next one, I want 3 significant digits. 3 sig figs, as we used to say. So I go 7708900. Well, I want it in scientific notation, so I start at the 7, the next is a 7, the next is a 0. So there's my 3, 770, right? No, because that digit 8 is going to make that 0 become a 1. So it becomes 7.71 times 10 to the what? Oh, we got to start at the 0 on the right. I go 1 to the left of the first 0, 2 to the left of the second 0, 3 to the left of the 9, 4 to the left of the 8, 5 to the left of the 0, and 6 between the two sevens. So it becomes 7.71 times 10 to the 6th. Now I want two significant digits. So it's the decimals on the left side, and there's a 0, so I start at the 7, and then I have 7 and 0. The next digit's a 4, so I really don't care about the rest. So it's 0.70 would be in normal notation, but I want that in scientific notation, so I move the decimal 1 spot to go between the 7 and the 0, so it becomes 10 to the negative first. 7.0 times 10 to the negative first. Now, in order to do units of measurement, we have to look at what makes science numbers different from regular numbers. Living in America makes things very difficult because most of the world, most of the scientific world, uses something that we call SI units. SI units are based from metrics. Metrics is easier than regular numbers that we use, the English system, because the metric system is all based on multiples of 10, which is basically the same thing we did with scientific notation. 10 to the 7th, 10 to the 6th, 10 to the 3rd. Those are very easy because you're just multiplying by multiples of 10. So the standards that we use in science is a different type, and they're called the International System of Units, or SI, because it's a French word, and that's a revised version of the metric system. And it's based on tens, and it makes things much easier. The prefixes are easier. You don't have to worry about, okay, how many centimeters are in a meter? Well, centi means 100, so there's 100 centimeters in a meter. How many millimeters in a meter? Well, milli means 1,000th, so that would be 1,000 millimeters per meter. So here's a table of some quantities that are what we call the SI base units. They are the base units for different measurements. From these units, we can then derive or make up different units. For example, length is meters. Well, the unit for, or the abbreviation for meters is M. Mass is in kilograms. That means kilo means 1,000, so that means it's 1,000 grams. Volume is in cubic meters. Well, a meter is like a meter stick, but you put it front, left, and down, and that gives you a cubic meter. So it's a meter times a meter times a meter. Time is in seconds. Energy is in something we call joules. Pressure is in what we call pascals. Electric units are in amps or amperes. Temperature is different. In SI units, it's Kelvin. Most times we're going to be using Celsius, but Kelvin is a special unit that we will use in this chapter, or this unit, sorry. The amount of substance in chemistry is something called a mole. And the abbreviation is just chopping off the E. I don't make the abbreviations, I just use them. And luminous intensity is how bright something shines, and that's in candela, from candles. So those are units. You're not going to have to memorize them. It's just, these are the units. If you want to see how long it is, we use meters. How heavy it is, we use kilograms. How much space it takes up, so forth and so on. So the first thing we're going to talk about in our SI units today is temperature. Temperature is how hot or how cold something is. When you have two different objects at different temperatures that come in contact, heat is going to move from the object at a higher temperature always to the lower temperature object. For example, you put a frozen steak on the counter. Well, the counter's at a higher temperature. So what's going to happen is the frozen steak's lower. The heat from the counter is going to absorb into the steak to cause it to thaw. The same thing if you put ice in a glass. The glass is usually warmer than the ice, so the ice is going to melt inside the glass because the heat from the glass will then warm up the ice cubes. The Celsius scale is what we use in chemistry, and that's a very simple scale because they use the freezing point of pure water. When water freezes, they called that 0 degrees Celsius. When it boiled, they called that 100 degrees Celsius. And it was very simple because, see, then you just have division of 100 slices between 0 and 100. You don't have to worry about the Fahrenheit and what's this and what's that. Fahrenheit is crazy. We're not even going to go into that. Another temperature scale that we use is called Kelvin, or the absolute scale. Kelvin scale has the freezing point of water at 273.15 kelvins, and the boiling point is at 373.15 Kelvin. Now, the figure below shows how Kelvin and regular Celsius are compared. 0 Kelvin is called absolute zero. It is the point at which no movement in molecules happens. It is a theoretical spot. You cannot actually heat something down to, or I should say cool something down to absolute zero. And that's equal to negative 273.15 degrees Celsius. That's 273 degrees lower than the freezing point of water. So I'm going to let the guy take over for a second, and he's going to explain something that's special about absolute zero. Kelvin temperature is the absolute temperature. All right, because 1 degree Celsius equals 1 Kelvin, converting from one to the other is quite easy. K equals C plus 273, or degrees Celsius equals K minus 273. But the one that we usually use is, because it rhymes, is K equals C plus 273. So normal body temperature is 37 degrees Celsius. I want to know what that's in Kelvin. So what I want is K. I have 37 degrees Celsius. That's not a negative. That's a dash between the H and the 37. So now I take my equation. K equals degrees Celsius plus 273. And I'm going to interject the 37 into the degrees Celsius. So the degrees Celsius is 37. The difference between Kelvin and Celsius is 273. So 37 plus 273, human body temperature is 310 Kelvin. That's 310 degrees above the absolute coldest temperature that can exist. So, I got a few problems for you. Silver melts at 960.8 degrees Celsius and boils at 2,212 degrees Celsius. Express these in Kelvin. So the first thing is I need to know that K equals C plus 273. And then what I'm going to do is, to get the temperatures, I'm just going to plug in 960.8 as you see in the first equation. Add that to 273, it's 1233.8. Then 2212 plus 273 is 2485. Now, the next one, liquid nitrogen boils at 77.2 Kelvin. That's pretty low temperature. What is this temperature in degrees Celsius? Well, we're going to use the opposite equation. C equals K minus 273. Now, I mistakenly put 77.3 instead of 77.2, but instead of adding 273, we're going to subtract. So when I subtract 77.3 and then I take 273 from that, I get negative 195.7. If you did it correctly, you would have gotten negative 195.8. Now, we're going to talk about density. Density is something that is very commonly covered in science classes. And what I have here on the right-hand side is what we call density column. I took normal things that you would find around the lab and I placed them into this column. And the thing on the bottom that looks very cloudy, that's corn syrup. Its density is 1.4 grams per cubic centimeter. That's the most dense liquid in this entire column. So that goes on the bottom. Above that is this detergent, which is a density of 1.1. So it's a little bit less dense. So guess what? It's going to float on top of it. Water is on top of that, and I put blue food coloring in so you could see that layer. Otherwise, it would be hard to see the mix between the water and the vegetable oil. The vegetable oil is clear, and that's 0.92, so oil floats on water. And the last thing on the top is rubbing alcohol. Rubbing alcohol has a density of 0.79, so that's even less dense. That would be at the top. So the higher the density, the lower in the column. Now, if you were to just shake this up and mix, because of the certain things, they would mix up, especially with the dish detergent in there. But as long as you keep the things in the column steady, you can actually get this nice 5 layers from lowest density on the top to highest density on the bottom. What determines the density? Mass and volume. It's a ratio. mass divided by volume, D equals M over V. When you measure mass, mass is in grams. Volume for solids is cubic centimeters, because if you use cubic meters, you have to have a pretty big sample. So I have 4 samples here, and they're all 10 grams. I have 10 grams of lithium, 10 grams of water, 10 grams of aluminum, and 10 grams of lead. Now you'll notice that their volumes are different. The mass is the same, but the volumes are different. The density for lithium is 0.53 grams per cubic centimeter. So 10 grams would be divided by 19 cubic centimeters. That's why the sample looks the largest. Then you have the density of water is 1, so you have 10 grams over 10 cubic centimeters. The density of aluminum is 2.7, which comes from 10 grams divided by 3.7 cubic centimeters, and the lead is 10 grams and only 0.88 cubic centimeters. So if you are looking at them, you can see that their volumes are much different, but the masses are the same. And when you take mass divided by volume, that's where you get density. Now, matter is made up of atoms, and depending on how they interact, it affects the density. Most substances are going to increase in density as the temperature goes down, because as the temperature goes down, the particles move slower. As the particles move slower, they get closer and closer together. But water is an exception to this. As water gets colder, it does get more dense. Water is most dense at 4 degrees Celsius, just above its freezing temperature. When it gets to 0 degrees Celsius and starts to freeze, the particles rearrange and the density actually decreases. And that's why ice floats on water, because the density of ice is about 0.917 grams per cubic centimeter, where the density of liquid water at 4 degrees is exactly 1.0. Now we're going to do just a couple of density problems. I want the density when I have the mass of a copper penny, and its mass is 3.1 grams, and its volume is 0.35 cubic centimeters. So to do this, I have a special way of setting up problems. You see that WHH? W is what you want. H is what you have. So you take the word problem and you pull out what you want. What you want is always going to be usually in a question, and it doesn't have numbers. So it says, what is the density? So there's no numbers. So I have to figure out, where do I get those numbers? Well, the previous sentence has 3.1 grams, 0.35 cubic centimeters. So I have my mass, I have my volume, and I have my equation. Density equals mass over volume. So the first thing I'm going to do is I'm going to take density equals mass over volume, plug in 3.1 grams for mass, 0.35 grams per cubic centimeter, do my calculation. I get 8.8571 grams per cubic centimeter. But I look back, 3.1 has 2 sig figs, 0.35 has 2 sig figs, so I want to round that to 2. So I go 8.8, the next digit's a 5, so that 8 becomes a 9.
Water is the liquid of life. We drink it, we bathe in it, we farm, cook, and clean with it. It's the most abundant molecule in our bodies. In fact, every life form we know of would die without it. But most importantly, without water, we wouldn't have iced tea. Iced tea. Why do these ice cubes float? If these were cubes of solid argon in a cup of liquid argon, they would sink. And the same goes for most other substances. But solid water, aka ice, is somehow less dense than liquid water. How's that possible? You already know that every water molecule is made up of 2 hydrogen atoms bonded to 1 oxygen atom. Let's look at a few of the molecules in a drop of water, and let's say the temperature is 25 degrees Celsius. The molecules are bending, stretching, spinning, and moving through space. Now, let's lower the temperature, which will reduce the amount of kinetic energy each of these molecules has. So they'll bend, stretch, spin, and move less. And that means that on average, they'll take up less space. Now you'd think that as the liquid water starts to freeze, the molecules would just pack together more and more closely. But that's not what happens. Water has a special kind of interaction between molecules that most other substances don't have, and it's called a hydrogen bond. Now remember that in a covalent bond, 2 electrons are shared, usually unequally, between atoms. In a hydrogen bond, a hydrogen atom is shared, also unequally, between atoms. one hydrogen bond looks like this. Two look like this. Here's 3, and 4, and 5, 6, 7, 8, 9, 10, 11, 12. I could go on. In a single drop of water, hydrogen bonds form extended networks between hundreds, thousands, millions, billions, trillions of molecules, and these bonds are constantly breaking and reforming. Now back to our water as it cools down. Above 4 degrees Celsius, the kinetic energy of the water molecules keeps their interactions with each other short. Hydrogen bonds form and break like high school relationships, that is to say, quickly. But below 4 degrees, the kinetic energy of the water molecules starts to fall below the energy of the hydrogen bonds. So hydrogen bonds form much more frequently than they break, and beautiful structures start to emerge from the chaos. This is what solid water, ice, looks like on the molecular level. Notice that the ordered hexagonal structure is less dense than the disordered structure of liquid water. And you know that if an object is less dense than the fluid it's in, it will float. So, ice floats on water. So what? Well, let's consider a world without floating ice. The coldest part of the ocean would be the pitch-black ocean floor, once frozen, always frozen. Forget lobster rolls, since crustaceans would lose their habitats, or sushi, since kelp forests wouldn't grow. What would Canadian kids do in winter without pond hockey or ice fishing? And forget James Cameron's Oscar, because the Titanic totally would have made it. Say goodbye to the white polar ice caps reflecting sunlight that would otherwise bake the planet. In fact, forget the oceans as we know them, which at over 70% of the Earth's surface area regulate the atmosphere of the whole planet. But worst of all, there would be no iced tea. Iced tea.